almost certainly have an intuitive idea that for some processes, the rate at which the process happens depends on the quantity of stuff involved. Think about apple trees. Since rate is just a quantity per unit time, like your heart rate is the number of beats per minute, one apple tree can produce apples at a rate of 4 apples per year, whereas a bunch of apple trees can produce apples at a rate of 20 apples per year. Here, calculating the rate is just counting the number of apples produced each year. The more trees you have, the higher your rate's gonna be. But what if it's not that simple? Stick around to find out.
As a rather morbid example, consider this reaction. Car plus motorcycle leads to scrap metal plus broken glass. Obviously, the rate at which products are produced depends on the density of cars on the road and the density of motorcycles. Mathematically, we might write rate equals K times density of motorcycles times density of cars, where K is a constant and the square brackets represent concentration, as is the notation chemists use. This expression makes intuitive sense. We know that more traffic leads to more collisions. There are more frequent collisions during rush hour than on a quiet Sunday evening. The mathematical expression says that the presence of more of either reactant will increase the rate at which product is produced. More motorcycles leads to more scrap metal and more broken glass. The expression also says that if you have no motorcycles, there will be no products produced, regardless of how many cars are on the road. Similarly, if you have no cars, there will be no products produced, regardless of how many motorcycles there are. Again, consistent with our experience. Of course, one can get scrap metal and broken glass from collisions between two cars, but that's a different reaction. Note that this is a one-step reaction. A car and motorcycle go bump, and that's it. You have scrap metal and broken glass. The cars don't turn into something else first. Car and motorcycle, then scrap metal and broken glass. No intermediate stuff along the way. Such a one-step reaction is called an elementary reaction. We will return to this important technical point later. By contrast, let's consider the process by which a beverage bottling plant produces product, 6 packs of bottles of soda or beer or whatnot. In this case, the rate depends on how fast the assembly line runs, not how much reactant is available. The warehouse might contain 80,000 empty bottles, or 8,000 empty bottles. It doesn't matter. 6 packs get produced at a constant rate, until the bottles are all gone, of course. There could be vats full of beverage, or just a few liters remaining. It doesn't matter. 6 packs get produced at a constant rate. Mathematically, we might write rate is equal to K, where K is a constant. For reasons that should become clear shortly, a chemist might write rate is equal to K times quantity of beverage to the 0 power times quantity of bottles to the 0 power times quantity of caps to the 0 power, which is exactly the same expression because anything to the 0 power is 1, making this seem like a silly way to write the rate. But hang in there. Here we show a single-step reaction with one reactant. In this reaction, A simply converts to product. The rate expression shows that the rate of reaction is proportional to the rate constant K and the concentration of the reactant. This is said to be a first-order reaction because the rate depends on the first power of the reactant concentration. Note that this is a unimolecular reaction because the fundamental reaction step involves one molecule. For a single-step reaction with 2 reactants, A and B collide and produce product. This is analogous to our car plus motorcycle example. The rate of production of products depends on how much A is present and how much B is present. If either is not present, the reaction cannot happen and the rate of production of product is 0. This is said to be a second-order reaction because the sum of the powers of the concentrations in the rate expression is 1 plus 1, which is 2. This is a bimolecular reaction because the fundamental reaction step involves two molecules. The case where one A collides with another A to produce product is also bimolecular. Here, the rate of production of the products depends on the concentration of A times the concentration of A, which is simply A squared. That means that such a reaction is also second order, because the sum of the powers of the concentrations is 2. For a one-step reaction with 3 reactants, A, B, and C, the rate of production of products depends on how much A is present, how much B is present, and how much C is present. This is said to be a third-order reaction because the sum of the powers of the concentrations in the rate expression is 3. This is a termolecular reaction because the fundamental reaction step involves 3 molecules. This is extremely unusual. Usually a reaction involving 3 reactants takes place through multiple bimolecular steps. Reactions of higher molecularity are unknown. There are also zero-order reactions where the rate is independent of the reactant concentration. Those are analogous to the bottling plant assembly line process. The molecularity of the reaction refers to the number of species that come together in a single step, which is not necessarily the same as the number of reactants. A reaction with 3 reactants is not necessarily termolecular. What happens if the reaction does not take place in a single step? For example, consider this reaction between vinegar, that's acetic acid, and baking soda, that's sodium bicarbonate, in water. This is not an elementary reaction. It takes place through a complicated series of steps. In this case, the reaction rate does not depend on the product of the reactant concentrations. It is not termolecular, it is not third order. We can't write the rate law just based on the overall reaction. How then do we express reaction rate? How do we know the order of the reaction? In general, for a multi-step reaction, the rate expression can only be determined experimentally. In this experiment, we are going to show you how to determine a rate law experimentally. How are we going to do that without a laboratory? By finding the rate law for liquid leaking out of a vessel. We call this experiment rate law for a leaking whiskey barrel. Before we dive into the experiment, we need to look at the theory. Consider a cylindrical vessel full of water but with a small leak in the bottom, so the water is dripping out. How fast will the water level, H, drop over time? To figure that out, we need to do some mathematics, mostly just AP level calculus. It helps to know what a differential equation is, but you can learn enough along the way, so that isn't essential. As always, you can revisit this section later if you miss something important. According to the Hagen-Poiseuille law, the rate at which fluid passes through a small tube is proportional to the pressure, where rate is defined as the volume passed per unit time. From general physics, we know that pressure P is defined to be force F per unit area A. In this case, the force is the mass m of the fluid times the acceleration due to gravity g. The force is negative here because it is in the downward direction. The mass of the column of water is given by its volume times the density ρ. Since we have a cylinder, the volume is the height of the column of fluid H times the cross-sectional area A. Crossing out A shows that pressure is minus rho g h. If we let K prime be the constant of proportionality between rate and pressure, we can define the rate as K prime times rho times g times h. Note that since the cross-sectional area of our cylinder is constant, the change in volume may be written as the area times the change in height. Moving A to the other side of the equation shows that rate is simply minus a collection of things that are constant times h. Defining a new constant k yields a simple expression for the rate. Making the time interval infinitesimal yields the instantaneous rate law. Look at that. After all that algebra, we find the system obeys a first-order rate law. In this case, we know the instantaneous rate law, but how can we determine it experimentally? The instantaneous rate law gives the rate at any point in time. Experimentally, one does not measure the rate at which a quantity is changing, one measures the quantity itself. For example, in a chemical reaction, one doesn't measure the rate of change of concentration, one measures the concentration. Here, the quantity that is changing is the height of the column of water. We can measure the height, so we need an expression that gives height as a function of time. To get a function that gives the height of the column of water as a function of time, we are going to solve this little differential equation. To do so, let's get everything involving height on one side of the equal sign and everything involving time on the other side. This is called separation of variables. We can then just integrate each side. To connect to physical reality, we apply the limits of integration. The height is h naught at the initial time t equals 0 and h at the final time. Solving the integral and substituting the limits of integration yields this form. Next, we apply this expression from algebra. A little rearranging produces the form we seek, the height of the column of water as a function of time. Experimentally, this isn't the most useful form, though. This is. This expression is of the form y equals m times x plus b. If we plot the log of the height versus time, we will obtain a straight line, the slope of which is minus k. It should look something like this. Experimentally, if we have data recording the height of the column of water for a series of time points, we can plot the log of the height versus time. If the data are linear, that confirms the process obeys first-order kinetics.
For this experiment, you will need a straw where you can clearly see where the water is inside. A transparent straw is preferable, but even a fast food straw will work because you can still see the water line inside of it. And no, sorry, your metal straw won't work for this. A ruler, tape, both masking and clear if possible, a cup, ideally with a pouring snout, a pan, or something that could catch water leaking out of a straw, a timing device, ideally one that beeps every 5 seconds. We actually used a YouTube video, which I've linked in the description. A location with access to water and a sink, a computer with spreadsheet software, a sturdy stack of books/boxes about a foot tall, a wire at least as long as your straw. If you don't have a wire, 2 straightened paper clips twisted together should work. A pen and paper, paper towels, a pin or small paper clip, a sandwich bag, hot glue, scissors, and a camera. The one on your phone will work nicely. To set up this experiment, you'll want to create your own leaking whiskey barrel. In this case, it'll look more like a burette. Take a piece of tape and cover your ruler like this. Try to cover as much of the ruler as possible while still leaving the numbers visible. Next, take a small piece of tape and use it to cover one end of your straw. Fold down 4 edges and then pinch the corners like I'm doing here. Do your best to make a good seal. Now take that straw that you just covered with a piece of tape and attach it to the ruler you taped earlier. If you have hot glue, you can do it like I'm doing here by running a bead of glue along the ruler up against the numbers and placing the straw right on top, with the taped end hanging off the end of the ruler at 0 centimeters. If you don't have hot glue, you can use tape to do the same thing. Clear tape is preferable because you can see through it, but either way, try to tape it near the top of the straw and adjust the straw so that it's as straight as possible along the numbers. Next, you'll need a place to mount your straw and ruler. We used a pile of textbooks and a box with a weight in it. Whatever you use, you'll want your stack to be sturdy so it doesn't fall over. It's also helpful to have a bit of an overhang on your stack, so that when you mount your straw and ruler, a pan can fit nicely underneath to catch the water that's going to drip out of the straw. To mount your ruler to the stack, take a piece of tape and put it right above the top of your straw. Then secure your ruler near the top of your stack, making sure that there's enough room between the bottom of the ruler and the table for a pan to slip underneath. When you mount the ruler, do your best to keep it as vertically straight as possible. With a different ruler, measure the length of a little nub hanging off the end of the ruler with the straw taped to it. Write this number down, you'll need it later. Next, you'll need something to use to fill your straw with water. We found a good way to do this is to cut the corner off of a sandwich bag and fill the bag with water, and then use the stream of water coming out to fill the straw. Make sure you make the hole really small because you want your stream of water to be really small. If you don't have a bag, you can use a cup. Just be ready for spillage. Once you're ready to start the experiment, take your wire and place it down into the straw. Then take your cup or plastic bag and start filling the straw up with water. Work your wire up and down to get all of the air bubbles out of your straw. Once all the air bubbles are gone, remove the wire from the straw completely and take your finger and place it over the top of the straw to keep the water from dripping out. Next, get your camera, remove your finger from the top of the straw, and film the water line dropping through the straw as the water drips out of the bottom. Make sure to keep the camera level with the water line at all times so you can get a good reading off of the ruler. Also, you don't want the water dripping out of the straw too quickly or too slowly. If it's dripping too slowly, use a pin to make a small hole in the tape. If it's dripping too quickly, take the tape off altogether and put on a new piece. There is a lot of flexibility with this. Here, the water's nearing the end of the straw, so it's dripping kind of slowly, which is perfectly fine. Don't worry too much about trying to get the drip rate perfect. You just don't want it falling so fast that you can't get enough data, or so slow that it's taking 20 minutes to go a couple centimeters. Stop your video when the water is near the end of the straw. Don't bother trying to video the straw until it's completely empty. Near the end, the dripping is likely to be unstable anyway and mess up your data taking. Play your video that you just took of the water falling through the straw and start your timer. Using the timer, stop the video every 5 seconds and record the height of the water in the straw using the markings on the ruler. The timer I'm using here is a YouTube video that beeps every 5 seconds. So I'm starting the timer, and then when I hear a beep, I play my video. 5 seconds later, when I hear another beep, I pause my video and the timer. Then looking at the paused video, I record the height of the water in the straw. When doing this, make sure you're recording the height from the bottom of the meniscus of the water in the straw. Once I've written down the height, I'll start the timer again, and when I hear a beep, I'll play my video. Then, 5 seconds later, when I hear another beep, I'll pause my video and the timer and record the height of the water in the straw again. I repeat these steps until the water's near the end of the straw and I've had enough data. Again, don't try to take data until the straw is completely empty because the dripping rate is unstable at the very end of the straw and it will likely skew your data. Then you'll need to input your data into a spreadsheet. In the first column, you'll put the time. Start at 0 and go up by 5s. In the next column, you'll input the height of the water inside of the straw, which is the data you just took. I lied. The data you just took is not the actual height of the water inside of the straw, but because if you'll remember, there was a little nub of the straw that hung off the end of the ruler. So in the next column, you'll input the actual height of the water inside of the straw by adding the length of this nub, which you should have written down earlier, to all the numbers you just recorded in column B. In the last column, you'll record the natural log of the height of the water inside the straw, which you'll do by doing the natural log of the numbers you just recorded in column C. Now you'll want to plot the natural log of the height versus the time. To do this, select all the numbers in column D and all the numbers in column A and insert a scatter plot. Then insert a linear trend line, and you can display the equation of that line and the r-squared value on the chart. The r-squared value will tell you how linear your data is. R is what is called a correlation coefficient. The closer r squared is to 1, the more linear your data is. As you can see, we did pretty good here. And because our data is linear, we now know that the water leaking out of the straw obeys first-order kinetics.
How is this experiment related to chemical reactions? Consider this reaction. If it is a single-step unimolecular dissociation, it should obey this rate law. That's mathematically just like the rate law for the water drop experiment. A plot of the log of the dinitrogen pentoxide concentration versus time should yield a linear plot with a negative slope. It does. The reaction is said to be first order since it depends on the first power of the dinitrogen pentoxide concentration. In general, if we plot the log of the concentration of some species X versus time and obtain a straight line with a negative slope, we know that the reaction is first order in X. This is how information about the rate law is obtained from an experiment. We will leave it as an exercise to work out the integrated rate laws for the case of a zero-order reaction. You should find that a plot of concentration versus time is linear, and if you are more ambitious, the case of a second-order reaction. Have fun!